moving on with solar, we're going to look at some of the positives and some of the challenges with solar energy. So first, just the potential of sunlight is probably the best of all of the alternative sources that we've looked at. So let's just sort of take a dive into that. So we take the number we've used a bunch, right? And so the solar constant of 1360 watts per meter squared. And so we take this, and again we subtract out the part that reflected, the 29.3% reflection loss. And then again, when we're doing this, it's watts per meter squared. So let's just multiply by pi r squared. So again, the area that the sun sees of the Earth when it's delivering energy. And with this r, this is going to be the radius of the Earth. So we're talking 6,378 times 10 to the 3 meters. So 6,378 kilometers. When we figure this out, we get this huge number, 122.8 times 10 to the 17 watts. And what we like to do with this number is put it into terawatts, because that's going to be our most useful comparison. So I'm going to take this and then convert over to terawatts. And so 1 terawatt is 1 times 10 to the 12 watts. And when I do this, I get 1.23. We'll truncate that times 10 to the 5th terawatts. And then just the way to write that is going to be most helpful is out like this here. So 123,000 terawatts. And why do we write it in terawatts? Well, because we know that right now worldwide usage power is about 18 terawatts. So when you look at this number, this is really exciting, right? The solar potential out there is huge. And again, we were saying this is basically one of the best, at least potentials of all the renewables. And so let's maybe dive into this a little bit more. All right, so let's dig into this a little bit more. So we have this number, 123,000 terawatts. And let's go through and multiply this by a few things. So first, multiply it by 0.15. And this is for the photovoltaic efficiency. As we've mentioned, these things are about 15% efficient, so they don't get all of the sun's energy. They get about 15%. Then let's multiply by 0.29%. And that's the total percentage of land mass of the world. So, assuming that it doesn't be too helpful to put these in the middle of the ocean. And then with all that, let's just say, okay, we take about 10% of the land mass for solar cells. Okay, so where does that leave us? Well, it's actually pretty good. It's about 535 terawatts. Again, remember that our sort of goal right now, our energy use worldwide power is 18 terawatts. And so this is pretty good. And so what we can do then is take this 10% and look at it. Well, so this is somewhere in the neighborhood of about 25 times more than we need. And so let's divide this by 25. And when we do this, we get 0.04, which again leads us to about 0.4%. So a nice number. We only need somewhere in the neighborhood of 0.4% of our land mass covered in solar cells to basically replicate the energy use we have right now. So that's a pretty good, this sounds pretty promising to me. It's just to kind of show you, this is how big we're talking about. So it is sizable, but still compared to all the land mass we have, it's still pretty tiny. All right, so this seems like a done deal. Let's get started. Why? How come we're not there yet? Well, there are downsides, and so primarily the first one is cost. So right now it's about 38 cents per peak watt when you buy a photovoltaic cell. And so if we wanted to say to match 10 terawatts of worldwide energy with solar, so again we're going to assume that most places get about 4.8 full sun hours a day, which is 20% of the day. And so if you wanted to get the capacity for 10 terawatts, you would need 50 peak terawatts of photovoltaics. And this is, of course, worldwide. So at 38 cents per peak watt, this comes to about 19 trillion. Now, but you also need to pay for installation and such, and so that roughly doubles it. And so we're talking something like $40 trillion if we were to sort of snap our fingers and try to do this in 1 year. Again, the global economy is about 110 trillion, so you're talking about over a third of the global economy. And then by contrast, humans spend about 1.5 trillion a year on oil, so substantially less. And so this is, we talked about how fossil fuels are cheap. I know that sounds weird, but then when you make these comparisons, this is sort of what we're talking about. And then to make it even, hit home a little bit more individually, to cover our individual energy use as an American, remember that number is about 10,000 watts, we would need about 50,000 peak watts, which again translates somewhere about $40,000 to $50,000 per person. So, a lot of people, I think, not sort of an easy thing to do, I think, by snapping your fingers. Some other downsides, so again, this 0.4%, while pretty small, is sizable. Then there's intermittency, which is basically that you're getting energy during the day when there's sun, but our energy demands don't match that, and it's even worse for people who have worse winters than us. And so, more than likely, if you were to do this, you would need some sort of battery storage, which we'll talk, but makes this even more expensive. And then finally, all energy is not equivalent. There's some things that just solar doesn't seem to work super well for. So it's not going to be this great solution. And so these are just some of the reasons that, 40 years after the first photovoltaic was invented, they still produce less than 1% of our energy. Just as mentioned, right, a typical household uses much or most of its energy when the sun is not shining. So things like cooking, evening entertainment, charging your EV, whatever. And so you would more than likely need to have some sort of local storage. Right now, most people who have solar at home are grid tied, and so they actually use electricity from the grid at these times. And so again, you would need some sort of storage and batteries, and we'll talk a little bit about what that does to cost. And so let's go through and just try to add up some numbers for what we would need to do individually for this sort of thing. So here we go back to this chart we saw earlier. Right here that says that for our residential use, we're using about 11.9 quads, right? Q BTUs, and this is about 40% of this comes from electricity retail. And so that would mean that for us, then 42% of 11.9 Q BTUs. So again, 0.42 times 11.9 quads gives us about 5 Q BTUs, which you can convert over to joules, which is 5.3 times 10 to the 18 joules. And then what we do is we take this number and divide by the total number of seconds in a year, which is 3.15 times 10 to the 7 seconds. And we get a huge number, 1.67 times 10 to the 11 watts. And so this is, again, sort of the power that we're using here in our country. And so we then take that number, 1.67 times 10 to 11 watts, and divide by the number of households, which is roughly 130 million. So 130 times 10 to the 6, we call those households. And so this gives that each household's energy use is about 1,285 watts. And then I'll just sort of write that as 1.285 kilowatts. And so that's our power usage. And so for energy in a day, then what we would need to do is take that 1.285 watts times 24 hours, and that gives about 30 kilowatt hours. That gives us something to aim for as far as our energy needs. And so let's design a grid-tied PV system for an average U.S. household. Again, PV is photovoltaic. And so since we do have kind of an advantage here in San Diego, let's look again somewhere like St. Louis, Missouri. And so there's this chart in the book that says, again, that if you, by sort of doing different panel tilts, you can actually get close, even in a place like that has, again, some disadvantages, to the 4.8 kilowatt hours per meter squared per day. And so that's sort of great news. And so what we can do is just sort of estimate in a place, again, like St. Louis. And so let's assume that we have 18% efficiency. And again, we'll take this number, the 4.8 kilowatt hours by meters squared. And we want to find, okay, what area would I need for my house in order to meet my energy needs if I, again, lived in St. Louis. And so we set this equation up. 0.18 times this gives me a number of 0.864 kilowatt hours per meter squared. This is again per day. Both of these numbers are per day. It's our energy use per day. And then just define that again, that area. And so when I calculated this out, I got a number of about 35 meters squared, which translates to about, since we use feet, 400 square feet, which again that's kind of nice news in that it would fit on a lot of houses, which is a good thing. But let's look and again try to start thinking about cost a little bit. Now, when thinking about cost, you've got to go into this and think about it more in terms of peak wattage. And so in that case, what I'm trying to do is you can think about this in terms of 4.8 peak sun hours that we have. So if we have 4.8 peak sun hours, right, what peak wattage do I need to equal 30 kilowatt hours? And again, this is watt hour, and here we end up with watt times hours. We got the same on both sides. And when I plug this in, I get my number is 6.25. Again, peak kilowatts, and so you can sort of round that up to 6.3 kilowatts. So again, the pricing for this is in terms of peak wattage, not square meters. But it's nice to know that it can fit on a house. But we can use this here to actually look at costs. So again, just sort of following the arguments from the text. So again, to meet our needs, we would need about 6.3 peak kilowatt hours, the size of a PV system. But unfortunately, it's not quite that simple. So to be smart about this, you would probably need to add about 20% because the panels get dirty. They don't always operate at their peak temperature, and there's just various efficiency losses. And so you're talking about needing a 7.5 peak kilowatt power system. Then you need to multiply 1.5 for the winter months because there's going to be a time when you just can't. Because in the winter there's a much larger imbalance there. And so then you're talking about 11.25 size of a system. And then off-grid. So again, to really do this effectively, you want to get rid of the grid. And so they suggest another increase of 1.5. So now you're talking about a 17 kilowatt PV system. So then you take that and then multiply by $3. So we're talking that installation, everything is about $3 per watt. So $50,000, again, which sort of jives what we were looking at before. But then the battery generally doubles this cost. So then you're talking about $100,000. And so very quickly, again, these are all upfront costs. And so, the same electricity right now costs about $4.5 a day. So if you figure this out, the savings, right, it takes pretty substantial time to sort of get payback for this. And then the other unfortunate thing is that this payback time very likely would exceed the lifetime of the batteries. So this is really some of the sort of down and dirty to why this is not so easy as it might seem when you look at the solar potential. All right, then it's nice just to kind of look and see what's happening right now. And so this is the actual PV density, so sort of how many milliwatts per meter squared production there actually is in the United States. And so again, there's a couple states like California, Nevada, and Arizona a little bit that are using this. Worldwide, we're still, like we were saying, getting less than 1.5% of all of our energy from solar. Another way to look at this is in terms of the capacity factor, and this is the ratio of actual performance to the peak possible performance if the thing was going at its peak all time. And so here in the U.S., so it doesn't look too bad, but this is sort of looking at where we do have solar. What sort of capacity factor does it have? And it's sort of variable. Again, it sort of peaks. No one's doing much higher than like 28%. But just kind of gives you a picture of where things are with that. So just to kind of summarize solar energy, the pros and the cons. Solar taps into a super abundant resource. The PV technology has no moving parts. These panels themselves can last a long time. We've shown that we can actually fit this on rooftops, and many people are providing self-contained electricity already. The life cycle CO2 emissions are much less than fossil fuel. And again, the technology works and it's been deployed. The cons, the intermittency, right? So it's difficult to balance the grid if the PV was the majority or only source of electricity generation. So we would need storage batteries, and as we discussed, that would at least double the cost. PV is still expensive compared to fossil fuels, especially in terms of upfront costs. Electricity alone is not great for certain things like transportation and some industrial applications. And then PV manufacturing involves environmentally unfriendly chemicals. Now again, just the caveat that these things are getting cheaper, and that this is something that many smart people are working on, right? So the hope is that this news will get better over time.